Hmm. Right. Hello. Those of you that are here. Um, hmm, 7, 8, 9, 10. Yeah, sure. This should be, we might be a little bit shorter today because I think everybody in year 10 and 11 did the same thing. So there'll be fewer things to go through. Right. Let's begin doing this. Face that away. 7, 8, 9, 10. Right. I presume this is where we are. Yeah. Okay. Um, any other questions? Just let me have them. So, the table and histogram show some information about the cholesterol level in the blood of 100 hospital patients. Electric motors, yeah, I'll do that as well. Yes. Okay. Um, the table and histogram show some information about the cholesterol level in the blood of 100 hospital patients. Um, we have some frequency 0 to 2, 2 to 3, fine. Remember, as soon as you see a question about a histogram, the thing to think of is frequency density. Yeah, I'll send those notes. I'm not sure why they weren't my mistake. Um, 9, 10, 11 on the yeah, I think that's well, so if I'll do 7, 8, 9, 10, and 11 basically now, and then that'll be both booklets. I think they're the same. Um, so the thing to think about with histograms is frequency density. Frequency density is your frequency divided by the width of the group. That's the way I think of it. If you're did the key stage 3 one, or you wouldn't have done this stuff, just so you're aware. Um, but to work out frequency density, then it is the frequency 8 divided by the width of the group. The width of the group is 2 here, so 8 divided by 2 is 4. Here we've got 13 divided by 1, so it's 13. We don't know what it is here. We'll come back to it. Here it's 19 divided by 1, so it is 19. Here we don't know because we don't know the frequency. This is 15 divided by 3. 15 divided by 3 is 5. So they're the ones I know. And then we also, you always have the same questions here. You have to use the table to complete the histogram and then use the histogram to complete the table. It is always the same sort of thing. So we have a missing bar here between 2 and 3. And now I know that the 2 and 3 bar has to go up to 13. So 13 is going up in twos, is it? 12, 12, 13. So I think it's there. And so you will have a bar that goes between 2 and 3 up to 13. That is that bar. Then the 3 to 4 will come back to. The other missing bar is 4 to 5. 4 to 5 goes up to 19. So you would continue here, go up to 19 and down. Um, and then that's that one done. Is there another one? 7 to 10, bar missing. So 7 to 10 goes up to 5. Remember, you're going up to the frequency density, not to the bar. So 7 to 10 goes up to 5. So that's where you're going up to, right? So 7 to 10, 5 is there. 7 to 10, the bar is wider this time because that's what histograms do. They have a width which controls that. Alternating the down. Yeah, fine. So there's a bit of electromagnetism seems to be the common theme, which I can go over the notes on that afterwards. Right, so that's that. So we're still not filled in the table yet. So we've got these two gaps to fill in. So the 3 to 4 bar, when you have a histogram already drawn for you, then the area of the bar represents the frequency. So if I need to know what frequency is between 3 and 4 here, then I need to know the area of this bar, this rectangle. So it goes across 1 and up to, geez, 17, I think. Yeah, up to 17. Right, so it's up to 17. So it's 17 times 1, which is 17. that is the frequency of the people in that bar. So that is 17 in here. 5 to 7 is also missing. Now that's a width of 2, and it's gone up to 14, it looks like to me. That's 14. So 14 times 2 is 28. So you're finding the area of the bar, the height by the width. So that 28 goes into here, which means that that is everything completed, I believe. Yes, it is. Right, question 8. Yes, I will do year 9, question 4. I'm just have to do this a little bit first. We'll have to wait. In fact, let me just see what it is. Because if it's relevant, I can just get it out of the way now. Okay, yeah, let's just do this while we're here. The pie chart shows information about how year 10 students travel to school. I've got a feeling there's a problem in this question, but we'll see. Mark with the letter the probabilities of each of the following. The student walks to school. Okay, well, walking to school is a quarter of this circle. So I would go with, well, it's a quarter, isn't it? So that's why A is there, because that's a quarter of the scale. That's a half. That's 3/4. I have to guess this. The student does not walk to school. So does not walk to school is all of this bit, which is 3/4 of this circle, which means that B goes there. And the student travels by train. Well, train isn't even in this diagram, which means the train must be 0. I've got a feeling we can't do this question without a protractor. 40 students travel to school by car. How many year 10 students are there? I think it is almost impossible to do this without a protractor. So I think what you have to do is measure this angle here with a protractor. Let me see if the mark scheme tells me anything. Yes, so apparently, if you use a protractor to measure this angle, you will get 60 degrees, which is essentially what you need, because 60 degrees is 1/6 of this circle, because it's 1/6 of 360 degrees. It's 1/6 of the whole circle, which means that if 40 students travel by car, then the rest of the circle is 6 times as big as that number. So you do 6 times 40, which means the whole circle is 240 people, and 1/6 of it, which is this section, is 40 people. So it should have really told you, but that is what you had to do there. And then there's 252 students in year 11, the same proportion walk as in year 10, work out the number. So in year 10, we know that a quarter of them walk to school because it's a quarter of that circle. So if it's the same proportion, it's still a quarter. You do a quarter of 252 will give you the number of year 11 students. A quarter of 252 is 63, I think. Yes, so that's 63. Right, I can move on. Question 8. Anna plays a game with an ordinary fair dice. If she rolls 1, she wins. Okay, well, it's an ordinary fair dice. The probability of rolling a 1 is 1 out of 6, isn't it? Because there's 1 on a dice. If she rolls 2 or 3, she loses. So the probability of rolling a 2 or a 3 on a dice, because there's 2 of those numbers, is 2 out of 6. And then if she rolls 4, 5, or 6, she rolls again. So that means that's 3 numbers out of 6. Okay, so 3 out of 6 is a half. That's why we put a half over here already. So just double check that this adds up to 1 whole, which it does, because that's a half and there's another half. And we're going to roll again. So if we roll again, we're here, which means we're going to have 2 more, so well, more branches coming out. When she has to roll again, if she rolls an odd number, she wins. There are 3 odd numbers on a dice, 1, 3, and 5. If she rolls an even number, she loses. There are 3 even numbers on a dice, so you can put a half. I've just put 3 out of 6, just to make it clear. Is Anna more likely to win or to lose? You must work out the probability that she wins. Okay, so what is the probability of winning? So As it says here, if she rolls a one, she wins. So that's a win. But if she rolls a two or a three, she loses. And then if she rolls an odd number, she wins. Okay, so in order to win, there are two ways to win as far as I can see. You could just roll a one on your first roll. The probability of that happening is 1 out of 6. So that's one way of winning. Another way of winning is to go this way and then this way. Okay, so roll a 4, 5, or a 6, which has a probability of a half, and then roll an odd number, which also has a probability of half. So I'm going to change that to a half now. So because these are the two different ways of winning, so either you could get 1/6 the first time, so roll a one, or you could do it a different way, so this way and then that way. Because there's two different ways of doing something, you add their probabilities together. And 1/6 time add 1/4 1/6 add 1/4, you should be able to work out. So that is 10/24. Um, I'll answer your question about Eid in a second. Is Anna more like, sorry, I haven't answered the question yet, more likely to win or to lose? Well, if that's your probability of winning, isn't your probability of losing the rest of it, which is 14/24? So she's therefore more likely to lose this game rather than win this game. So yeah, there you go, 10/24. So she's more likely to lose this game because that's a bigger number. That's a bigger probability. Um, and that is that. Right, 9. I'm doing to 11, aren't I? Okay. Right. Joanne has a fair five-sided spinner. What's the probability of scoring a 4 with one skin? Because it says fair, it's equal chance of all of them. Probability of rolling spinning a 4 is 1 out of 5, isn't it? 1, 2, 3, 4, 5. It's 5 sections. What's the probability of scoring a total of 4 with two spins? With two spins. Okay. So in order to get a total of 4, you could get a 3 on your first spin and a 1 on your second spin. Or you could get a 1 on your first spin, a 3 on your second spin. That's a total of 4. Or you could get a 2 on your first spin and a 2 on your second spin. They are the same as either way around. So these are the three different ways, I think, of getting a total of 4. And what you have to do is work out the probability of each of these happening and then add them together. So getting a 3 first is 1 out of 5. Then getting a 1 is 1 out of 5 because there's only one of them. Or is the same again, 1 out of 5 times 1 out of 5. Or you could get a 2 the first time. Now, because there's two twos, that's 2 out of 5. And then the other 2 is also 2 out of 5, which changes the question a little bit. Just be careful. I've got to squash this all in a bit. 1 out of 5 times 1 out of 5 is 1 out of 25. One times that is also 1 out of 25. And then this is 4 out of 25. If you do 2 times 2 is 4, and 5 times 5 is 25. Once you've got the three separate bits, add them together. Because the denominator is the same, you can just add the tops and you get 6/25 as the answer. There, hopefully. Question 10. An ordinary fair dice is rolled. Once again, a fair dice, so it's just 1, 2, 3, 4, 5, 6. Complete the tree diagram. For landing on a 4. Okay. So we've spun it once. Spun, roll. Okay. 1 out of 6 is the probability of getting a 4. Not 4, must be 5 out of 6 because there's 5 other numbers that do that. Um, um, question 6 and 10. Okay, I'll come back to that afterwards. And then when we do it all again, it's the same, right? Nothing has changed. So it's 1 out of 6 and 5 out of 6, 1 out of 6 and 5 out of 6. Okay. What's the probability of the dice landing on 4 both times? So once you've done your tree diagram correctly, you just need to follow the path. So landing on 4 both times is that way. And your two probabilities times together. And that's it. 11. Some animals are twice as, oh God. Some animals are twice as likely to have male babies as female babies. Explain why the probability of a male baby is 2/3. Well, probably because the female baby would be 1/3, and 2/3 is twice as big as 1/3. I'd write that down. So 1/3 of the probability of a female, 2/3 the probability of a male. And That's the only way that that's going to be 2 times as big as that. One of these animals is expecting two babies. Fill in the tree diagram, 2/3, 1/3, 2/3, 1/3, 2/3, 1/3. Okay, see here. Done that. And then a scientist wants to predict the likely outcomes for the baby's genders. Which is more likely? Two of the same gender or one of each? That's be quite a lot of marks, this. Okay. Um, okay, well, two of the same gender. How do you get two? So what we do is the way I would explain this is to go, okay, more questions here. Five here, I'll come back to five. Um, Same gender. It's quite complicated, this question. So same gender or one of each. We need to figure out these things. Now, how could we get the same gender? We could get two males or two females. That's the same gender. What's the probability of two males? It's 2/3 times 2/3, which is 4/9. What's the probability of two females? It's 1/3 times 1/3, which is 1/9. And you would add those together. So when you have several options here to get the same gender, there's two different ways of getting the same gender. You add their probabilities together. 4/9 add 1/9 equals 5/9. Right, one of each. Right, again, what you need to do is write down the ways in which you can do this. One of each gender means that you could get a male and a female, or a female and then a male from your two births, as it were. So to get a male and then a female, it's 2/3 times 1/3. So we go that way. Male, female. 2/3 times 1/3. Or add female, male. That's 1/3 times 2/3. You could just do it once and double it, because I think it's going to be the same thing. But that is 2/9 add 2/9, which is 4/9. And so now you can see that this probability is more than this probability. So what's more likely is two of the same gender, because it's 5/9 compared to 4/9. That's it. Actually, I'm pretty sure you didn't actually have to do the second bit there. The reason you didn't have to do the second bit is because by default, if they're not the same gender, they're one of each gender. You see what I mean? Because so therefore you could have just done, well, if that's 5/9, then the rest of it is 4/9 because there's no other option. Okay, that was all of that. Right, let me just go back to question 5. Box plot. The median is the middle value. I think, and this might be just specific to you, I've got a very, very weird thing in the back of my head that box plots aren't in IGCSE maths, but you'll have to just double check that. I've just got this something in my head because I'm sad and remember things. The median value is this value here. Okay. Which is the middle of this box is the median. 22, 4, 6, 8, 28. Okay. And that's it. That's question 5. Right, fine. That's the median. Is there more? No, there's no more to question 5. Right, let me go back and do year 9, question 6, and I presume you mean question 10 as opposed to year 10. Question 6. Okay. The table shows the proportion of left-handed and right-handed students in a school. 20 boys and 10 girls are chosen at random from the school. Estimate the number of left-handed students chosen. It's a tricky question. Well, of the 20 boys, you would expect 15% of them to be left-handed. So you work out 15% of 20, which is 3. Yeah. And then of the 10 girls, you would expect 12% to be left-handed. So you do 12% of the 10 girls that you're choosing. 12% of 10 is 1.2. Now, obviously, you can't have 1.2 girls, but because it's just an estimate, I would just call that 1 and 3. So 3 add 1 means that an estimate is that out of your 30 people, 4 of them will be left-handed. That's it. Okay. And there's an equal number of boys and girls in the school. Work out the probability student is right-handed. I think all you do I'll double check this. I think what you do is you take the probability of a boy being right-handed, 0.85, and times it by the probability of a girl being right-handed. And I think that's what you would do for that question. Um, yeah, that's it. Because it's we need, yeah, that's it. Oh no, wait a minute. No, I think it is actually 0.5 times 0.85 plus 0.5 times 0.88. Okay, I know that sounds more complicated than what I said earlier. But the reason for that is that firstly, what you need to do is figure out whether you're going to get a boy or a girl. So there's a 50, let's pretend this is a boy. There's a 50% chance that you picked a boy. Okay. Out of because there's an equal number of both of them. That's why it tells you that. So the 50% chance you picked a boy, and then you then multiply it by the probability of that boy being right-handed, which is 85%. Or you could have picked a girl, which is why I'm now adding something. The probability of picking a girl would have been 0.5, and you times that by the probability of a girl being right-handed, which is 0.88. That calculation on your calculator should get you there. That's quite a hard question. Don't worry about it too much. Um, and 10, I think, is what you've also said. Oh, right. Estimate of the mean. Okay, so when you get one of these frequency tables and you have to work out the mean amount per customer, um, what you would do is do midpoints. So that's why there's another column here. So if you want to go to the middle of a group, sorry, if you've got a group, then you should go to the middle of it when you're doing these questions. So the middle of 0 and 10 is 5. The middle of 10 and 20 is 15. The middle of 20 and 30 is 25. Now, there's no middle to more than 30. But if you think about what we're about to do next, once we've got the midpoint, we multiply the number by the midpoint. Now, because this number is 0, conveniently, it doesn't matter what this number was, because when you multiply it, you're going to get 0 anyway. So that's why that's there. 18 times 5, I'll see if I can do this in my head, is 90. 15 times 15 is 225, I think. 7 times 25 is 175. If you add all of these together, that is 490, I think. If you add them up, so you add up this column, and then you do 490, which is what everything adds up to, divided by how many there were. And how many there were is the sum of this column, which is 22, 30, 40, I think. 490 divided by 40 is 49 divided by 4, which I now will use a calculator for, which is 12.25. That should be the mean amount spent per customer in that question. That is the process that you follow. Right. In answer to the, well, what I'll do is before I move on to, I think that's it for the maths bits, but I want to talk briefly about a topic called electromagnetism in physics, which is to do with motors and things, but I'll talk about that for 20 minutes or so. But before that, the question about Eid on Sunday, I think we're going to send an email just tomorrow. The simple answer is that the lessons are on as normal on Sunday. But if you can't make it or aren't going to be there, then let us know, and then there'll be some options to join another lesson. Although it's a little bit complicated because it's the end of the month, and as you know, we do like English at the end of the month. And we don't have that many replacement lessons for it. But let us know, and we'll see what we can do. It might be that if you are attending on Sunday, it might be best that you try and join on Saturday. So if you let us know early-ish, then there'll be potentially options to join on Saturday instead. I've just got a feeling that if you leave it till after that, that leaves only Monday. There might be one option on Monday, but then after that we change back to biology. So it's a little bit weird this month. Anyway, hopefully that answers the question. Right, let me talk about this topic. If you are in year 9 and still here, then you'll feel free, but this stuff you won't need to know for a little while, which is to do with magnets and the complicated bit of magnets. Um, okay, so Okay, so we'll start with this thing called a motor effect, and then we'll talk about those dynamos and things 'cause they're a bit more complicated. Um, oh, B for number 10. Apologies. Did I miss something? Oh yeah, I did. Sorry. Using the till receipts, the manager works out the actual mean amount spent for each group. Um, okay. Without further calculation, decide whether the actual mean will be different from the estimated mean in part A. So we got £12.25. Uh, Less is the answer. The reason it's less is because what did we do in part A? We took the midpoints, didn't we? We did 5, 15, and 25. We took the midpoints. And so we based our calculation on as if everybody spent that much from that group. But as it turns out, that they actually spent less than £5. And these ones actually spent less than £25. They spent exactly 15, so that's great. But the other two groups spent less than what we guessed that they spent. So therefore, our mean, or the actual mean, must be lower because they actually spent a bit less. And that's the reason, essentially. Okay. Right. The motor effect. In terms of what it is, I think my best illustration of this, firstly, I'm going to do my quick explanation of hopefully what we'll do, is this. This is what you're looking at in this picture is the motor effect. The motor effect is when a wire, which is carrying a current, suddenly just moves by itself. It experiences a force in the direction of that blue arrow. That's what happens. The reason it happens is because, as you hopefully know, any wire that is carrying an electric current has a magnetic field around it. If we just take this, um, if you could illustrate that, it would be like this, right? There's like a magnetic field around any wire that's carrying a current. And if we put that wire, which has a magnetic field, in another magnetic field, which is what we have done here, we have got these two magnets and they have a magnetic field between them. Then we have a magnetic field here and another one here. And those two magnetic fields interact. You want to try and use that word, interact with each other, causing the wire to experience a force. And the wire experiences a force. It's a little bit like when two magnets repel each other with the north and north poles. It just there's a force, right? It just appears. And so these two magnetic fields interact with each other, and the wire experiences a force. So that's the simple thing in terms of what the motor effect is. Now, there's two things you can do with this information. Number one, you can work out the size of this force. A force is measured in newtons. There is a formula on the physics formula sheet about it involves the magnetic flux density. There's a F equals Bill. So the force on this wire will be the magnetic flux density times the current in the wire times the length in the wire. So you could get asked a question about the size of the force. That's one thing. You can also then be asked about the direction of the force. So, for example, if I hadn't put this arrow up here and I said to you, draw an arrow that shows the direction the wire will go in, how do we know it doesn't go that way or that way or that way? Do you see what I mean? Why does it only go this way? Well, that's because of this Fleming's left-hand rule thing, which maybe you can see or not, I don't know. But there's a picture of it here. Um, so that's what I just said, calculating the size of the force. I can know this off by heart. Fleming's left-hand rule, though, comes next, which is this, right? So you put your fingers in these sort of positions, right? The crucial thing to remember is that there's a right angle, like between the first and the second finger, and your thumb and your first finger, there's a right angle. And then you rotate your wrist, basically, until you get it where you need to get it. And what this will allow you to do is work out the direction in which that force will be. You point your first finger, they try to help you here by saying F, is the first finger, and you point it in the direction of the magnetic field. The magnetic field is the direction from the north to the south pole of the magnet, as is this case here. So I can't do this clearly, but anyway, yeah, I can't really do that. So that's what you do with your first finger. Your second finger, you then rotate your wrist until your second finger is pointing in the direction of the current through the wire. And then wherever your thumb is left pointing is the direction of that force on that wire. That's what the motor effect is, or that's what Fleming's left-hand rule allows you to do. It allows you to figure out the direction of that force. You just need to get your pointing in the right directions. So an illustration of that would be here. If I said to you, here is a question, draw onto this diagram the direction in which the wire will go, because it'll experience a force. It will experience a force because if it is carrying a current, once again to repeat myself, if it is carrying a current, there is a magnetic field around this wire. There is also a magnetic field between this north and south pole. Those two magnetic fields interact, and there is a force on the wire. But what's the direction of the force on the wire? Well, you get your hand in such a position. You point your first finger in the direction of the field from north to south, as is being illustrated with my mouse at the moment. North to south, this direction, this direction. You then rotate your wrist until your second finger happens to also be pointing in the direction the current is flowing. The current always flows from the positive end of the wire to the negative end. And so it will be pointing upwards. And then your thumb is left, pointing in the direction of the answer. There is the answer. The force is going to be that way on the wire. Now, in order to begin to introduce the motor question in a second, if I, for some reason, swapped the direction this electricity was flowing, so for example, if I change that to a plus and change that to a minus, it means that the current is now flowing in this direction, which means that what I would need to do with my hand is swap it so that the second finger is pointing downwards, right? And when you do that, your thumb will end up pointing in the complete opposite direction. If you just imagine if I do that way and then swap it over, my thumb's now pointing in the opposite direction. And so that's important to understand, that if you change the direction of either of these two things, either the magnetic field or the current, the force will go in the opposite direction. Which leads us on to how a motor actually works. A motor is literally just something that spins. It is in like every single toy in the world, right? Something that spins. But how does it work? Well, what we do, it's also in everything else that spins, like a washing machine or a dryer or a drill or a fan or an electric toothbrush. So what we do is we get a wire, but crucially, we loop the wire. So the electricity will flow all the way around and back. Okay, so because we then put it in the middle of a magnetic field, there will be a force that the wire experiences because it's just going to be that motor effect that I've just been describing. But because of the fact that the electricity will basically flow, this is very slow. If you just follow my pen at the moment, oops. The electricity will flow in the direction that I'm going in at the moment. Okay. And by definition, it is flowing that way on the way there and this way on the way back. They are in different directions. And as I showed you with Fleming's left-hand rule thing, if you have changed the direction of the current, your thing changes, your thumb changes. So the force on the wire changes, which means that this side of the wire will experience a different directional force to this side of the wire because the current is flowing in a different direction. Let's continue with the picture. And that is what's shown here. So this side of the wire experiences a force upwards, and the other side experiences a force downwards, which means that we begin to loop, because that's what this is. The motor is about spinning thing. Someone's asked a question. Yes, plus to net. Yes, correct. So electricity always flows from positive to negative. And just on that note, if you have no visual clue in the question as to which is positive and which is negative, there will almost always be a battery, which is the circuit symbol for the battery. And in this circuit, if that is a circuit with nothing in it, the electricity will definitely flow this way around because the big line represents the positive terminal, the little line represents the negative one. And so we know it goes that way around this circuit, so this way. So yes, it is always positive to negative. That is always the direction. Although I know in this diagram, they have not specifically shown that, but they've given you the arrow that it's going in, right? So this is going in this direction and it experiences a force. And you can use Fleming's left-hand rule to check this, although I can't do it here because it's impossible for me to show you this properly. But if you point your first finger north to south and your second finger sort of left to right, as it were, your thumb will be pointing upwards. And then on the other side, you'll swap your current over and your thumb will be pointing downwards. So one side of the wire experiences an upward force, the other one experiences a downward force, which is where we begin to get the looping from. So if I push up one end and down the other end, then we're going to start spinning it, right? You see what I mean? That's what's going to happen. And that's what the motor effect is, except for we get a problem. And this is where the technical bit begins, which is that if we continued just pushing one end and pushing the other one down, so different directions, then when it gets to halfway, you're going to get stuck, as this is showing you, because you're going to have a force upwards and a force downwards, and it won't keep spinning. So what you have to do, every time it reaches this position, we have to swap the directions of the current. So what we're going to do now is swap this so that this is now going to flow the other way and then swap this. So this is going to go the other way. Now, if we swap the direction of the current, we will swap the direction of the forces, which means that now this will continue to loop round. And then every time when it reaches that halfway point again, we'll swap them again. And what this will do is we'll keep on getting it to spin. So the technical bit of this really, I think, is understanding that every time we reach a half turn, we need to swap the direction of the current. And the way we do that, and this is the technical thing, you don't have to know this in too much detail, but we use something called a split ring commutator. All that does is it swaps the current direction every half turn. So every half turn was a term. Which means that the positive becomes a negative and the negative becomes positive every halfway, which means it swaps the direction that the current is flowing in and it keeps your loop going round and round and round and round. And that's the only bit that's a bit technical. Okay, so if we didn't do this, it would just spin for a bit, but then get stuck. So now what we need to do is swap the direction of the current so that it continues to spin. But then if we still didn't swap it again, it would get stuck again. So we have to keep on swapping it every half turn. And so this diagram now does not show this very well, but the idea is that we continue to rotate because this thing keeps on changing the direction the current is flowing, and mainly because this keeps looping around as well. So this keeps looping around, which means that the positive becomes the negative, and it swaps the direction of the current. So that's the slightly technical part of that. 4-mark question on explaining. Oh, that's a good question. Well, I would say that's a good question. If there was a 4-mark question on this, we'll have to find it first. But I would have thought, I would say that it depends where we begin, I suppose. I mean, you could begin at the point where, I mean, it depends where we begin. So you could go, well, the wire carrying a current has a magnetic field around it. That interacts with the magnetic field between the magnets, which creates a force on the wire. But then I would say that one side of the wire, the current is flowing in one direction, and on the other side, the current is flowing in the opposite direction, which means they experience forces in different directions. So one side of the wire experiences a force upwards, for example, the other experiences it downwards. Then I would just say one more thing is that, and that causes it to start to loop, then I would explain that every half turn, we need to reverse the direction of the current. That's it. I wouldn't even mention the split ring commutator. I would say that it needs to swap every half turn. The generator effect, I think I'm about to come to, which is the next bit. Oh, I can't remember where does this bit come? So it was, yeah, okay. I mean, we're literally about to talk about generator effect. We're going to talk about alternators and dynamos. So the generator effect is the generator effect equal to change in magnetic field? I don't know. It sounds a bit vague. I mean, this is the generator effect. This is the illustration I use of the generator effect. So just to be clear, we've finished with the motor effect. This is now a different effect. They are sort of linked, but in the motor effect, you need an electric current to already be flowing because that creates the magnetic field on around the wire, which interacts with the other magnetic field. In the generator effect, we are generating the electricity. It is not already there. That's important distinction. Um, so what you can see here is a wire connected to a bulb. But there is no battery, there is no source of power, yet the bulb is lit up. How can that be? Well, that can be because this magnet is moving. Now, when you move a magnet through a coil of wire, we generate a voltage in the wire, which gets the charge flowing, which means that we get current and the bulb lights up. But why does that happen? Again, not I don't want to get too technical about it, but the magnetic field, let me do a picture again. The magnet has a magnetic field around it. Okay. Now, as we move this through the coil of wire, the magnetic field or the wire cuts the magnetic field. You see what I mean? Literally, not literally, but you know what I mean? It's cutting through it, it's passing through it. Um, and when it cuts through it, that generates a voltage in the wires, basically. It causes the charge to start flowing. Um, and that's it. And so when it's flowing, we get a bulb lit. So we only get it lit while the movement is happening. So we get this. If we keep on moving the magnet, we will keep on getting the electricity and the bulb will stay lit. If we stop, the bulb will stop being lit. That is ultimately the generator effect. And you'll notice that there's not a huge amount of technicalities in here, other than to say, um, yeah, the generator effect happens when a conductor, which is the wire, cuts through the magnetic field lines. And so we get the induction of electricity, or the electricity is generated, basically. Um, so when you said change in magnetic field, sort of, yes. So it is the result is that we get this voltage or potential difference being produced, and it is experiencing a change in magnetic field because of the movement of the wire. Can they ask a question about energy transfers on the generator effect? I don't know. I mean, yes is always the answer to that question. But the uh, I don't think so. I'm going to say no. I'm going to say no. I don't think so. Energy transfers are more basic in terms of just chemical to kinetic, or the other sort of stuff. But in this case, I guess if you really wanted to answer it, it is kinetic energy converted to electrical energy, right? It's literally what a wind turbine does. That's what's going on here. We this, if you imagine a wind turbine connected to this magnet, it's going to keep spinning when it's windy. And as it keeps moving, we're going to generate electricity because the bulb will stay lit. It's the movement that we need. And that is what the wind turbine is doing. Inside a wind turbine, we basically just have one of these. It's called a generator. This is a generator. It is doing the generator effect. So it should link all of your physics knowledge together a little bit when you talk about this. So all the way from energy at the beginning now to electromagnetism at the end. This is what's going on in a wind turbine when it spins. And that's why we get electricity, clean electricity from a wind turbine. Um, and then, I mean, I suppose the only other bit of this, a little bit, is to talk about this. So generators make use of the generator effect to induce a current. This is the generator, just to be clear, inside the wind turbine, effectively. They rotate a coil in a magnetic field. As the coil spins, a current is induced in the wire. Whether they generate an alternating or direct current depends on the device. So we have an alternating current here. Remember, this is going to be spinning around, around, around. Yeah, this is the spinning. And they generate alternating current. Their construction is similar to a motor, so that's very similar to what we saw a minute ago. However, something is causing the spinning this time, as opposed to electricity like the wind turbine spinning. As the coil spins, a current is induced in the coil. Every half turn, this current changes direction. Alternators use split. Yeah, so essentially, it's almost the same as the motor effect, except the spinning is happening as a result of like the wind. So it means that we get the electricity flowing one way, but then when we reach the halfway point, it starts flowing the other way because the split ring commutator change switches to the other end. And so we get an alternating current because it goes one way and then the other. So that's what an alternator is. It generates an alternating current. Whereas a dynamo begins with D, and therefore it generates direct current. They're similar to alternators with one difference. Um, they use a split ring commutator, whereas this uses something called a split ring and brush. So the contacts don't swap every half turn. Whereas here, they swap every half turn. So it's very similar to the motor effect again, um, to keep the current flowing in the same direction. So in this one, when it reaches the halfway point, because we don't swap anything, it automatically goes the other way. And so that we get an alternating current. Where in the dynamo, we want it to keep going in the same direction. And so we deliberately swap the contacts using one of these split ring commutators. That is a complicated explanation, I appreciate. But I'm trying to see if I can say something else about this. Yeah, I think we need to find some videos on this to help with this. But to put it very, very basically, if you want to remember one thing, an alternator generates alternating current. Um, and a dynamo generates direct current. So the current doesn't keep on changing direction. Um, we just get direct current in a dynamo. So they use a split ring commutator as their contact. Anything else to say about this? There's not much to know. Like literally, alternators and dynamos are just fit on the page you're looking at right now. So don't stress about it overly. This is it. It's not like it's going to be a massive amount of information. Um, but but it is a little bit to try and remember. Crucially, alternating current, direct current, alternators and dynamos. But both of them are generating electricity. They are part of the generator effect. So we are not using electricity here. We're just creating the spinning in something like a wind turbine. Hopefully that is something. I will send you the notes on this thing later, and I'll also get the electricity stuff sent to you in the morning. Sorry, not the statistics stuff sent to you in the morning with the histograms bit in it. Right. I'm not gonna, I think nobody else has asked too many questions. So on that basis for today, I think I will do just a reminder, if you do have any other specific things ahead of a Wednesday or even your weekly lesson, you can send it. I'll put the WhatsApp number on the email I sent today. So if you don't have it, you can, well, it should be on the back of every booklet. So you should have it anyway. So you can use that to contact us. Right. On that basis, I think I won't do any more today. Next week is going to be a little bit complicated because some of you are doing English over the weekend. So we're not going to do any English in the Wednesday session. So we'll just do something else. And if you have something specific you want to do, then tell me. But we may just do some more maths or anything, but just let me know. Statistics notes from Saturday. I will send it on the WhatsApp. I'll do that after this probably. But yeah, otherwise, I'll let you all go. And